Hey guys, let's try to solve this Leetcode problem 629, which is K inverse pair array. So first of all, what exactly is an inverse pair? Inverse pair are two integers whose indices and their values don't align. So for example, if you have I and j, let's take two indices I and j, and then how is it visible? Yeah, I and j, and then let their values a of I and a of j. So if I is less than j, and if a of I is greater than a of j, then it's an inverse pair, because the order of the value is exactly opposite to the order of the indices. So the question is, given two integers n and k, we need to return a number of different arrays which have values from 1 to n, which have exactly k inverse pairs. Okay, so what the question exactly wants us to find is, they'll give us two integers n and k. So imagine an array that has values between 1 and n, like 1 2 3 4 till n. We have to find total number of different combinations of, or you can call it permutations, of this array, so that they have exactly k inverse pairs. So we can read up the question once. So how would we even approach this question, huh? This is actually a tricky question. It's a bit hard. So here in Leetcode they gave us two examples. So for example, first example, one of the examples is n is equals to 3 and k is equals to 1. So in this case we need to find exactly, we have to find a number of permutations of array, of this array 1 comma 2 comma 3, so that it has exactly one inverse pair. So one inverse pair, so one inverse pair could be 1 3 2. If the permutation is this, it has like one inverse pair, like 3 and 2, like 3 is coming before 2 even though it's bigger than 2. So this is one inverse pair, and then we would have one permutation which is 2 1 3. Even in this case, like 2 and 1 form an inverse pair. So this is the question. How do we do this? So if you look at the constraints, the constraints are n can be up to 1, from 1 to 1000, and k can be from 0 to 1000. So looking at this, 1000, so it's like 10 power 3. So these constraints are like not really tight. These are like, like you can like use up to n square to solve this, because like n into k you can do, because it will still be 10 power 6, which is like, yeah, it's fine. So the one hint that I get from the constraints is you can solve this using some kind of brute force, or recursion or something like that. So how would we even do that? So one interesting thing about inverse pairs is they grow linearly. I'll give you an example. And given that, one advantage that we have is that the values in the array are 1 to n, so they are, we know what values we are going to have. So that is one advantage that we have. So so let's say we take an array of like 3 elements, 1 and 2. Okay, so now to place 3 in this array, we have like 3 places. We can place 3 here, or we can place 3 here between 1 and 2. We can also place 3 here. So if we see that if we place 3 here, there will be 0 inverse cases, because 3 is the greatest and there will be no inverse pairs here. So number of inverse pairs would be 0. And if you place 3 here, there will be exactly one number which is smaller than 3 and which is on the right side of 3. So you will have one inverse pair. And then if you keep it here, then both these numbers are smaller than 3, and then we are keeping them here. So there will be like two inverse pairs. So this is one interesting property of inverse pairs, that they grow linearly. In this case, only in this case, because the domain is really specific. That is, we have values from 1, 2, 3 up till n. So yeah. So yeah, we can think about, we can do this. So this like gives us a, this gives us a so let's say dp this, with these constraints you might like think, okay, we can solve this using dp or recursion. So thinking that, going forward with that, let's take the case, let's take this dp state, dp of oh, is it visible? Yeah, dp of m comma k. So what so how okay, so this is hard. Okay. Oh, okay. Let's like try this way. Let's say, let us say we already have an array. Okay, we already have an array of size n minus 1. Okay, 1, 2, 3 up to n minus 1. Now comes the question. Let's say now my task is to place nth array in this array. Like I have to place the nth array so that it has exactly k inverse pairs. Okay, so I have, how many options do I have? I can place my n here, then there would be no change. Let's say this so there would be no change in number of inverse pairs, because this is the biggest number, it's at the end, so the order is maintained, so there wouldn't be any more inverse pairs. Or I can place my n here just before the n minus 1. So in that case there will be one inverse pair, which is n and n minus 1. Or I can place it here, which would have two inverse pairs, three inverse pair. So let me define dp of n comma k as number of distant permutations of the array of size n, which has elements from 1 to n, and their inverse pairs are like k, is equals to dp of n minus 1 array. So if I place it at the end, so it won't change my number of inverse pairs. So if it's like n minus 1 with exactly k inverse pairs, that is fine, because if I add n at the end, it will still have k inverse pairs, plus dp of n minus 1 comma, if I place it like just before that, so I want that, then if see, imagine, so if an array whose size is n minus 1 and who has, let's say, k minus 1 inverse pairs, if I put the element just before the n minus 1, then the number of inverse pairs will increase to k. So we can use all these values, yeah. And then same with dp of n minus 1 comma k minus 2 until we put it here, which is at the start. So in that case, it might either be n, because, or k, depending on which is smaller. Does that make sense? Okay, let's try to code it out. So let's have a recursive function of which has like two arguments n comma k. So like if k equals to 0, that is if you want numbers with zero inverse, if you want an array with zero inverse pairs, that is like sorted array, so you only have one way. And if n is equals to, if n is less than or equals to 1 size, then you don't have any inverse pair, so there is no other way, so you have to return 0. And apart from that, so we start with I is equals to 1, and while I while I is less than or equals to n, because we don't want to like go beyond I is less than n, and we don't want to go beyond the like, I'll explain. And even k minus I should not be equals, should not be less than 0. In that case, if we have like answer, we can add it to like answer plus is equals to recursion of n minus 1 comma k minus I. So this is what we previously discussed, and we can return it. And then let's check this out. Oh, we have to do I plus plus. How long does it take really? Okay. Oh, it's failing one case. What case it might be? Okay, so if k equals to 0, what is this? Okay, return 1 if n is less than or equals to 0. Oh, we have to start from 0, because k minus 0, because we keep it, we also keep it at the end, like, so if we keep it at the end, then k equals to 0. Okay, see, so yeah, it works. But the problem with this solution is it's too slow, because recursion, we have like two arguments here, so which is like 1000 into 1000, and then we have one for loop inside, which might go at max up to k or n, like on the order of k. So it will be like n into k, which is like 10 power 9, which is like too slow. What do we do now? Oh no, we are stuck now. Oh, what do we do? But there is one but this is a really common, this is a, I wouldn't say common, but it's like this pattern is like, I don't know, this pattern is like quite visible. So I'm talking about this pattern. So if you see at like dp of, if you look at the summation here, it's like what, so if we like draw a, if I like draw a dp table with n going down and k going right. So let's say this is the nth row, okay, and this is n minus 1th row. So if we see, if I want to find like n dp of n and k, if I want to find this, so the summation is like n minus 1 k, which is this, n minus 1 k minus 1, so which is this, till last k elements. So if you look at this one common thing that you can see is these things, they are contiguous, like they are contiguous, like they are continuous values. So when we want to find always you have to when you want to find the summation of contiguous elements in an array, and you have to keep doing it, because you have to keep doing it for like for every n comma k, we have to keep doing that in the dp. So you have to keep doing that. You can use prefix sums. Prefix sums, it's a really quiet, it's a really standard technique that people generally use. I recommend you to look it up if you don't already know. So see, so each time going in a for loop and like finding the sum of these elements, what we do is we create a prefix sum. Prefix sum is like so I'm sure like okay, I think you have if you know what a prefix sum is, so I won't go really deep into that. So I recommend you to look it up. So prefix sum is nothing but we keep aggregating the sum, like dp of, okay, let's say prefix, we have an array of a of I, we have an element of 1 2, we have an array of 1 2 3 4. So prefix sum of this prefix array of this array would be like 1, and then 1 plus 2 2, and then 2 plus 3 3, and then 3 plus 4. So prefix of I will contain the sum of all the elements from 0 till I. So if you want to find the difference between this element and this element, I'll find the prefix of this minus prefix of this. So I'll get this element, because prefix is like 0 till that element. This is 0 to that element. So we can use prefix sum to find the array, find the sum, and then we can like our life would be easy. Instead of doing an O of n operation inside to find the summation, we can do that in constant time. But here prefix sum is not as easy. It's not as easy as as in general bottom up approach. This is a top down approach that we are using recursion, so we have to find clever ways to find the prefix value. So let's get back to our dp matrix. So n going down, k going right. So I want to find dp of this, okay, dp of n comma k, some n comma k, some n comma k. So instead of finding the prefix sum of this, what we do, but the thing is, the best part about dp is reutilization. We already know this value, we already know dp of n k minus 1, we already know this value, because if we have come till this point, we know all the values before that. That is something we have to assume in dynamic programming, and then like you keep assuming that you have, and you keep calling the cases, and they'll keep calling until it hits the base case. So that's like trust. You need to have trust that okay, you have this already. This is how top down approach works. So this is same, this would be, oh, let me use one different color. So this would be like this. Okay, so if we already have this value, so all we have to do is like subtract this value. Oh no, sorry. Subtract this value and add this value to this, then we'll get this. So we can write it like dp of n comma k is equals to, can you see the, okay, dp of n comma k minus 1, which is this element, which is this, and we have to add this to this, so that will be dp of n minus 1 k minus, we have to minus this, but this thing is, this can even leave before that, so generally it will be like dp of n minus 1 comma k minus n. But the thing is, we only have to do this if this like already doesn't go behind it. Like if this goes beyond it, then we didn't add anything, so we don't have to subtract anything. This, like, look at this. So this would be like the condensed prefix sum equation for dp of n minus k, n comma k. So yeah, does that make sense? You have to like go through prefix sum once, and then like look at this, like it's like graphical, pretty graphical. Let's try to write code with it. So if we try to do that, then there will be like n comma k, like the recursion will have two arguments, n comma k, which would make its time complexed as n into k with memoization of course, and inside that we won't have any for loop to calculate this sum. So it will be like linear, not even linear, like constant time, because we already know this value, we know this value, and we know this value. So let's get to the code. In the same code, like instead of this for loop, we can like write it as So answer is equals to dp of n, oh sorry, so we are using recursion here, so recursion of n k minus 1 plus recursion of n minus 1 k, and if k minus n is greater than or equals to 0, then we'll subtract answer minus is equals to recursion of n minus 1 comma k minus n, and then we'll return answer. Does that make sense? And then at the end we have to do recursion memoization. So we can, like, for doing memoization, you can use a you can use a cache array, or you can use a dictionary or a hash map to memorize all the values. But in Python we have this function called as cache. So you can get this from func tools. So you can, in Leetcode it's automatically imported, so you can just put @cache, so it will automatically cache the results. So it's equivalent to memoization. So let me run this. Oh no, I got a runtime error. Oh, got it. So I have to return it. We have the number can get quite large, so I have to keep modding it with 10 power 9 plus 7. So let me take a mod variable real quick. 10 power 9 plus 7, and then whenever I'm adding, I'll just do mod. I'll mod it with this thing. Yeah, there you go. Yeah, so this is I don't know, this is the hardest problem Leetcode has given Leetcode has given as a daily challenge this month. But yeah, it is quite interesting. It's like a perfect blend of, yeah, so it's like a perfect blend of DP and recursion and memoization, and most importantly prefix sum. Like, I know what prefix sum is, but it took me some considerable amount of time to come up with this prefix sum solution. Like, it's a really interesting problem where prefix sum and DP go hand in hand. It's a really good problem. I really enjoyed it. So tomorrow I'll be back with tomorrow's daily challenge. If you want to provide any suggestion, then yeah, let me know in the comments. Bye bye.